Hello. This lecture is going to give us a review of prime factoring. We're also going to be talking about prime numbers and composite numbers. But first, can you tell me why the dog crossed the road? He wanted to get to his barking lot. So we'll go ahead and get right into class. Factoring in prime numbers. Before you can talk about prime numbers, you have to know what prime numbers are. We have a definition up here of prime numbers. They are integers which are greater than 1, whose only positive factors are 1 and the number itself. Now we know that integers is a set of numbers that consists of all of the negative numbers, 0, and the positive counting numbers, if you will. 1½ is not an integer, 7/3 is not an integer, 2.683 is not an integer. They're numbers like we think of when we count sequentially. So in order for a number to be a prime number, it can't be negative, can't be 0, and it can't be 1. But any number that's greater than 1, that when you break it into factors, remember factors are the numbers that you multiply together to get the answer. But when you break these integers into factors, the only possible factors that are in there are the number 1 and the number itself. That's what prime numbers are. Now, composite numbers then are very easy. Composite numbers are non-prime. Non-prime means they're not prime numbers. Non-prime integers greater than 1. Greater than 1. Now I want to go ahead and highlight that because something that a lot of kids and a lot of adults have difficulty with when they're talking about prime numbers and prime factoring is they try to say that 1 is a prime number because the only factors of 1 are the number itself and 1. 1 times 1 is 1. They also might try to say that 0 is a prime factor. Not so often, but sometimes they do. Well, 0 times anything is 0. So we exclude 0 from the prime numbers, and our definition here specifically excludes 1. It says it has to be greater than 1. So when we talk about 1, it's not prime, it's not composite, it's just 1. Prime numbers have to be integers that are greater than 1. So now that you remember the difference between prime numbers and composite numbers, let's come up with our first few prime numbers. Well, they have to be positive numbers, and they have to be greater than 1. So what about 2? What factors are there for 2? Well, you can say 2 times 1 is equal to 2. Any way else that you can come up with that? No? What about 3? 3 is equal to 3 times 1. Factors into 3 times 1. Is there any other way you can multiply 2 integers together that are positive and come up with 3? No. Well, what about 4? Well, of course, 4 times 1 is equal to 4. Is there another way that you can multiply 2 numbers together and get 4? Sure, this is one of the easiest ones that you learn to multiply. You learn 2 times 2 is 4. So what about 5? What 2 numbers do we multiply together to get 5? Well, 5 times 1. Any other way? No. What about 6? Well, 6, of course, is 6 times 1. Is there another way? Sure. 2 times 3 is equal to 6 as well. 7. 7 times 1 is equal to 7. There's no other way you can come up with that answer. 8. 8 times 1 is equal to 8. See, we're using this multiplicative identity. The multiplicative identity tells us that when you multiply any number by 1, you always get that number back itself. But is there any other way that you can multiply 2 numbers together and get 8? Of course there is. 4 times 2 is 8. What about 9? Our multiplicative identity tells us that, but we also have 3 times 3 is equal to 9. So, you see the pattern that I'm doing here. I'm just going through and saying, what numbers can I combine together as factors to come up with our product here? Prime numbers are what? Prime numbers are integers that are greater than 1 that only have one pair of factors. So is this one prime? Yep, they only have one pair of factors. Is 3 prime? Only one pair of factors. Is 4 prime? No, it's not, because there are 2 pairs of factors. 5 is prime, 6 is not prime, 8 is not prime, 9 is not prime. And you will be using these prime numbers over and over and over and over again. So what I highly suggest that you do is that you multiply beyond a shadow of a doubt all of the prime numbers up to and including at least 31. So let me list those for you. And it's really not that big a deal at all. This is something, just like everything else, the more you use them, the more the values write themselves into your brain and become second nature. Your prime numbers are going to be not 0, not 1. They begin with 2, 3, 5, 7. You see that we've got a little bit of a pattern here, 3, 5, 7. They're the odd numbers. 9 is not prime though, because 3 times 3 is 9. 10, 11 is prime, 13, 15 is not prime because it is the product of 3 and 5. 13, 17, 19, 21 is 3 times 7, 23, 25 is 5 times 5, 27 is 3 times 9, 29, 31. Now let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I just threw in 31 as, 10 plus 1, so that you would learn these first prime numbers. Now, do you notice anything interesting about this list we have here? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. Notice anything? There's only one even number in there. Why are all of the rest of the prime numbers, and this is true for all of the rest of the prime numbers, why are they all odd numbers except for 2? Exactly. Any even number is divisible by 2. All even numbers are divisible by 2. So there will never be a prime number that is even, with the exception of 2, because the only factors that you have for 2 are 2 times 1. So 2 is prime. All other even numbers are not prime because they can all be divided by 2. It's going to be 2 times something. So those are prime numbers. Now what do we do when we're talking about factoring? Well, we've been doing some factoring, like 100 is equal to 10 times 10. Factoring just means taking a number and breaking it up so that it can be written as a product of numbers. What we're going to find is particularly convenient with algebra is that you write, and it's actually convenient in arithmetic too, but is that you be able to write numbers as products of primes. So let's say that we wanted to come up with the prime factorization of 36. This is called a factor tree, and we're just going to come up with 2 numbers. What 2 numbers multiplied together are equal to 36? It can be anything that you can think of other than 1 times 36, because obviously that doesn't help us at all. I'm seeing that my easel was about to fall down. There we go. 4 times what is 36? 4 times 9. Is 4 a prime number? No, because you can write 4 as 2 times 2. 9 can be written as 3 times 3. We want to keep breaking these individual numbers down. We want to keep factoring them until the numbers at the very end of each stem, if you will, they're all prime numbers. And this would be 2 times 2 times 3 times 3. 2 times 2 is 4, times 3 is 12, times 3 is 36. Is there another way that we can come up with the prime factorization of 36? Sure, what if I think that 36 is 2 times 18? 2 you can't divide further, it's already prime, so I'm going to circle it. 18 divided by 2, well, I'm going to think 2 times 9. 2 is prime, so I'm going to circle that. 9 is 3 times 3. What's another way that I might have done that? Well, maybe I said, okay, I know that 36 is 3 dozen eggs. 3 times 12. 12 is 3 times 4. 4 is 2 times 2. 2 times 2 times 3 times 3. When you're doing prime factorization of numbers, what you need to do is see what numbers jump out to you as an easy, as the quickest way to divide numbers. You don't have to follow somebody else's pattern. If you immediately see that's 4 times 9, go with that. 2 times 18, 3 times 12. Take your beginning number and break it up into prime factors, whichever way you see. Now, this particular method of prime factoring is not the one that I used the most when I was growing up, way back in the dark ages. What I liked to use was what I call upside down division. And I think they might call this a ladder method. But if we were going to divide 36 by something, that's how we do our division, wouldn't it? Well, I'm going to do upside down division. And I'm going to start always with the lowest prime number that will factor evenly into it. Do you have to do it this way? No, but it sure makes it a whole lot easier. You don't miss things. 36 divided by 2 is 18. Now I have a new number that I'm going to divide. Can I still divide 18 by 2? Yes. 18 divided by 2 is 9. Can I divide 9 by 2? Of course not. So I move up to the next prime number, 3. 9 divided by 3 is 3. The numbers that are on this outside here, these are the prime factors. So we say that 36 is equal to 2 times 2 times 3 times 3. These are the prime factors of 4. Now we want to write the prime factorization of 4 using exponents. Now, do you remember what we did with exponents? When we have exponential notation, we have a base and we have an exponent. And our generic way of writing that was to say x to the n. What does this mean? This means you take each specifically identifiable factor that there is. We have a 2 and a 3. We're going to take that specifically identifiable factor, which is 2. How many times is 2 used as a factor? Well, it's used 1 time, and it's used 2 times. And our exponent, that value that's represented by the n, is 2. So we have 2 squared times What's our next identifiable factor? What's 3? How many times is 3 used as a factor? It's used as a factor twice. So this right here, 3 squared, is equal to 2 squared times, I'm sorry, I think I said 3 squared. 36 is equal to 2 squared times 3 squared. This is the prime factorization, or the prime factored form of the number 36. We've expressed this as a product of primes using exponential form. It's that vocabulary. You've got to get to the vocabulary. I know it's tedious, but that's what you have to do. So this is what we're going to do when we are prime factoring numbers. Let me do just one more quick one for you. I'm going to do it 2 different ways. Let's say that we have factor 18 into primes. That's our instructions. Factor 18 into primes. 2 ways to do this. We can use our factor tree. I immediately think 3 times 6 is 18. You might think something differently. Is 3 a prime number? Yes, you can't say anything other than 3 times 1 is 3. What about 6? Is 6 prime? No, it's not, because 2 times 3 is equal to 6. 2 times 3. 2 is prime, 3 is prime. So 18 is equal to, now when you're lining your factors up, always start with the lowest prime number and continue in ever-increasing order. It's true that 18 is equal to 2 times 3 times 3, but if you are specifically asked to give the answers in exponential form, make sure that you read your instructions, exponential form. That's what this is going to be. 18. How many times is 2 used as a factor? 1 time. Do I have to write 2 to the 1? No, we can tell we're just using it 1 time. How many times is 3 used as a factor? 3 is used as a factor 2 times. So this right here is the exponential form. This answer here is correct. It is true that 18 is equal to 2 times 3 times 3, but it's not what they asked you to do. They asked you to give them the exponential form of the prime factorization of 18. So you could use a factor tree. You could also use upside down division. 18 divided by 2 is 9. You cannot divide 2 by 9, 9 by 2, but you can divide it by 3. Your outside numbers here are all prime factors. 2 times 3 times 3. 18 is equal to 2 times 3 squared. And clearly and necessarily, whichever method you use, if you're using legitimate methods and you're being careful with your arithmetic, you get the same result. If you do different methods and you get different results, obviously you have a problem. So play around with these. Learn your prime factors up to 31. Practice writing numbers as products of primes using exponential notation. That will get you on good, solid ground for algebra.